Between 2017 and 2021, a good heuristic was that if a robotics or AI paper was from a Chinese lab, it probably wasn't worth your time. So now, just in the last 2 years, I've really had to update my prior. The robotics and AI work coming out of China is like better every day. Technology changes real fast, and people are more willing than I'm usually expecting to take on risk. Autopilot and full self-driving is a good example. As of today, I don't think a labor replacement narrative is actually very well grounded in reality. The level of autonomy and technology required to create complete labor replacement is incredibly high and very far off. It's completely theoretical at this point.
Robots. Why care about them? How could they get a lot better at doing things? And how is the world doing on robots relative to China? To discuss, we have on today Ryan Julian, who is a research scientist in embodied AI. He most recently worked on large-scale robotics foundation models at DeepMind and got his PhD in machine learning at USC in 2021. Ryan, welcome to China Talk.
Thank you, Jordan. It's great to be here.
So Ryan, why care about robotics?
So the reason you should care about robots is that robots are the ultimate capital good. So, like a power tool or a washing machine or like some automated machine tool in a factory, a robot's purpose is to augment and multiply human labor. So therefore, increase human productivity. And the hypothesis is that societies which master robotics will enjoy higher labor productivity and lower costs in the sectors where robots are used, like logistics, manufacturing, transportation, et cetera. And those societies and their citizens will enjoy more of those things as a result. You could even imagine if we're able to make robots more advanced so that they're able to serve in domestic, office, like service sectors, then the implications for the economy and lifestyles of the people in those societies could be even more profound because we're increasing productivity in those sectors which are traditionally have trouble with productivity growth. So, instead of a robot vacuum cleaner, imagine the possibility of one day having a robot house cleaner or a robot home health aide or an auto mechanic. Now, these things are all pretty far off, but they're becoming less and less far off with every passing year. And if we kind of zoom out to like really broader societal trends, you think about, we're in the whole world, but especially rich societies have declining birth rates. And this question of what do we do to provide labor to a society whose working age population is continually shrinking. So, robots could be a possible answer for that question. And then as a sidebar, this is China Talk, so I want to make sure I address this, although I'm not an expert in this topic. There's, of course, military and geostrategic elements to this as well. Robots are a dual-use technology, and if they can make car production cheaper, they can also make weapons production cheaper. Then there's also the possibility of robots being used as weapons directly, and the implications that might have on and off the battlefield, right? So this is already happening in the war in Ukraine with drones. And from the perspective of a roboticist like me, drones that you're using in Ukraine as weapons are already very primitive, uses of robotics and AI. So you can imagine that if a company like Anduril wants to create this whole host of new, more intelligent robotic weapons with the actual state-of-the-art robotics, that could have huge implications. So I don't really have a ton of expertise in this area, but I wanted to acknowledge that. Sure. So in a sense, robots are no different than any other labor-saving machine or technology. They could be an ATM or an LLM, like we're all, really excited about. They're tools for multiplying human labor. The differences are in degree and physicality. So usually when we refer to something as a robot, we're imagining a machine which can automate a physical task, which we previously thought was impossible to automate. Because it requires meaningful and somewhat general, sensing of, reasoning about, and interaction with the real world. Right. So that's what makes it a robot instead of just like a machine. You need some intelligence. The thing needs to be interacting with the world. And so Waymos and Roombas are robots, but your dishwasher is just an appliance. And that's what we mean when we talk about robots. And that's why we should be so excited about them, because we could be bringing this labor saving and this greater productivity to sectors of the economy that were not thought possible before.
Gotcha. So we have this, we've had the world starting to grok this vision of, unlimited intelligence, right? And, white collar jobs getting completely automated because like anything you can do on a computer, maybe one day GPT-8 will be able to just do it better, faster, smarter. But the kind of, TBD. But for robots, we're defining that down to like things in the physical world that need to be moved around, manipulated with, bombed, whatever, that like need some kind of brain to do it. So
Right.
it's not this like automated repeating process of like, okay, like I pick up the apple and I put it in
Correct.
I put it in the bin to send to Whole Foods. It is
Yeah.
a something that requires like a little more brain in it, as well as this sort of physical capacity to do the manipulation or what have you.
Exactly, exactly. You need to be sensing, reasoning about, and then interacting with the world in a really non-trivial fashion, in a way that really requires intelligence. That's what makes a robot, or at least an intelligent robot. And I can also take what you said and kind of flip it on its head. The other way you can think about this, and this is just two sides of the same coin, is you can think about the role that robots are starting to move towards now is to become a body for that GPT-8, that embodied AI you're talking about. So right now, with LLMs and VLMs, we could do these incredible feats of purely digital automation, where you give it 1,000 PDFs and ask it to summarize them. But that same VLM maybe even be able to tell you, like, here's how you make a great cake. Here's how you bake a great cake. But it couldn't actually do it, right? It has no arms. It has no way of interacting with the world. It's and not, at least in real time, usually seeing like something in the real world. But if you were to take that machine, that large transformer, that GPT, and you were to embed it in a machine that actually could sense and interact with the real world, then that intelligence could affect not just the digital world, not just text and images and videos and audio on the screen. It could actually affect the physical world. And so some of the conversations we're having, for instance, about how LLMs and VLMs might affect like the legal profession or other like white collar areas, they could have the same implications for physical labor.
Ryan, why is this so hard?
So a couple reasons. One is that physics is a cruel mistress. Any robot has to exist in the physical world, and it has to correctly interpret and manipulate physical phenomena that have an incredible amount of variation. It needs to see. So imagine if you want to make a robot that works in any home. You need to be able to understand any home in the world, not just in a visual sense, but also in a physical sense. There are many shapes of doorknobs that are used throughout homes, and you need to know how to use and how to open and close a doorknob, any dorm in the world, in any home. So that's one reason is that physics is difficult. Physics also, the physical world has these properties that are different than the digital world. In the digital world, almost everything is reversible, unless you very intentionally make your digital system irreversible, like encryption. Anything you do in a digital system, you can reverse. You can delete. If you delete something, you can actually, honestly, usually undelete it. But also, if you make an edit in a Microsoft Word document, you can always undo the edit. If a robot knocks a cup off of a table and it falls down, and that robot does not have the ability to lean down and pick up the cup, it's now made an irreversible change to the world, at least irreversible from its perspective. This means that failure for robots can be catastrophic. You can imagine, like everybody has probably, who has a robot vacuum cleaner, has at some point experienced the robot vacuum cleaner like eating a cable or something and then calling for help. That's kind of like one of those irreversible failures. And the physical world is full of those. Yeah, I mean, so irreversibility in physics, those are the really, really big reasons. The other reason comes down to the maturity of the technology and the kind of the technological platform on which everything is resting. So something like ChatGPT or like Gemini or like DeepSeek, you feed it an image, you feed it text, you feed it audio, and all those signals are purely digital. Like nobody needed to build a monitor, a camera, a microphone for that to work. There's literal centuries of technology that this is sitting on top of, and we just take for granted that our ability to digitize the physical world works really well. And then and mostly what these systems are doing is data processing on existing representations of the physical world. The best way to think about robotics today is that we would like to do the same intelligent things that we're doing with Gemini or DeepSeek or Eagle or ChatGPT. But if you're a roboticist today, you gotta start, winding. The way that you can think about someone trying to build a robot is if you wanted to do ChatGPT, but you start by trying to make a CPU and then trying to wind the speakers and microphones for your machine, and you need to invent a digital camera so you can take digital images. Robotics is just emerging from the period where we're just trying to create the hardware that can turn perception of the physical world into data that we can process and use intelligently in the digital world. And then the other thing that's unique about robotics is that we have this reverse process where we have intent in the physical world, and we need to turn that into motion, action, touch, walking in the physical world. And robotics hardware is just getting to the point where building robotic systems that are relatively capable for doing those two activities is not only possible but economical.
Today's podcast is brought to you by 80,000 Hours, a nonprofit that helps people find fulfilling careers that do good. 80,000 Hours, named for the average length of a career, has been doing in-depth research on AI issues for over a decade, producing reports on how the US and China can manage existential risk, scenarios for potential AI catastrophe, and examining the concrete steps that you can take to help ensure AI development goes well. Their research suggests that working to reduce risks from advanced AI could be one of the most impactful ways to make a positive difference in the world. They provide free resources to help you contribute, including detailed career reviews for paths like AI safety technical research, AI governance, information security, and AI hardware. A job board with hundreds of high-impact opportunities. A podcast featuring deep conversation with experts like Carl Schumann, Ajay Kotra, and Tom Davidson. And free one-on-one career advising to help you find your best fit. To learn more and access their research-backed career guides, visit 80,000hours.org/ChinaTalk. To read their report about AI coordination between the US and China, visit 80,000hours.org/ChinaTalkCoord. That's 80,000hours.org/ChinaTalkCoord. Now back to the podcast.
So let's explore that of like the brain of like perceiving the world and understanding what to do, and then the kind of like physics of like the grabbing and the moving and the locomoting or what have you. Flying, whatever. Like how do those two technological tracks interact with each other? Do they progress? Does one go, maybe we can do this from a historical perspective of like, who's leaping ahead and who's the laggard over the course of the past few decades?
Yeah. So robotics is a in computing, it's a fairly old field of study. It depends on who you ask what the first people who study robotics were, but many of the sources will tell you it was probably like Harry Nyquist and Norbert Wiener, and these guys who were interested in this thing called cybernetics. And I'm bad with dates, but I think this is back in like the 50s or 60s. It's MIT CSAIL lab guys, and at the time, cybernetics, artificial intelligence, and information theory were all one field of study. And also control theory. So control theory goes off and becomes the field of study that allows you to do things like control state-of-the-art fighter planes. Information theory goes off and becomes data mining, databases, Google, and Oracle, and all of these, all this like kind of Web 1.0, Web 2.0 information processing, big data stuff. Artificial intelligence goes off and is kind of famously in the desert so it has a big revolution in the 80s, and then kind of has this the great AI winter from the 80s through like the late 90s, and then we with the whole deep learning revolution. And if you want to learn more about that, listen to more China Talk, and you'll learn about that, right? And then the last child is cybernetics, and cybernetics eventually becomes robotics. So the original agenda of this whole project was to create machines, thinking machines. That's actually where the company's name comes from. Thinking machines that could fully supplant human existence, human thought, and human labor, like a true artificial intelligence. And the original idea of this whole group of people was that you would need bodies in order to do this, right? These computers would need to exist in the physical world. So that other branch, cybernetics, goes off and becomes robotics. So robotics, the study of robotics is about 75 years old at this point. Now, traditionally, up through maybe, let's say, 2010, 2015, a huge amount of effort has been placed in creating the robotic system hardware that could actually reliably and with kind of enough power and enough dexterity interact with the physical world. Like literally, do we have motors that are powerful enough? could we put them together in a way that they could walk? So a big milestone in this area was the MIT Cheetah project, which was led by Sang-Bae Kim in around 2008 to 2012 era. And this gave rise to two things. It gave rise to this four-legged form factor you see on Unitree's four-legged robots, and also and now Boston Dynamics and all these. And it also gave rise to particular motor technology, so the way that we make motors for these robots. So you have the physical components of the robot. In addition to the physical components of the robot, you need sensing. So you need the ability to you need to be able to capture what the world looks like. You may need to capture the shape of the world, right? So self-driving cars have put a lot of time and effort into engineering 3D sensors like LiDAR so that we can make self-driving cars. And each of these little pieces have traditionally taken a long time to build up in the actual capabilities of the technology. So can you take the pictures? How big are the pictures? Can you actually sense the shape of the world? Can you sense the position of your own body? All these are requiring pretty difficult electrical engineering challenges and sensing challenges. And then once you have this machine, each of these sensors and each of these actuators, but in particular these sensors, are producing a lot of data. You need to move that data around and you need to process it. In order to process it, you need computation. So once we have the physical systems, the next thing and let's say the physical systems were there around 2010. Then you need enough computation on board to be able to turn those physical signals into information you can reason about, enough computation that you can reason about the signals to create motion. And you need to be able to do it on a moving machine. Now, this is where we cut where robotics. So, robotics has traditionally been a fairly niche thing. And so it hasn't, until maybe about self-driving cars, hasn't attracted a huge amount of capital investment. So the history of robotics is kind of a bunch of people trying to ride the wave of technological innovation in other areas, like computing. Actually, a big moment was for robotic motors was cheap brushless motors being used in electric skateboards and power drills. It just so turns out that if you modify those motors a little bit, they're really good for robots. But the fact that those got to a really high scale was actually really great for the cost of robots. And the same thing occurs along Moore's law and things like GPUs, right? So one of the reasons that robots are becoming more capable today is that the amount of computation you can pack into a small package and run off of a battery is becoming very high. It's becoming high enough that you can actually in real time process cameras, LiDARs, joint sensors, proprioception, all of these things, and do most of the critical computation in order to make a competent robot on board the robot.
Gotcha. And why does it need to happen on the robot? I mean, I guess you can kind of do the Elon weirdness of you have a bartender who's just being a robot from India. That doesn't really count though, right? I don't know. You tell me, Ryan.
Yeah. I mean, this is a great kind of debate or trade space people are playing with in the field right now. There are certain things which really need to be on the robot for physical reasons. So, and the framework you can use to think about it is on what time scale, on what deadlines is important that a robot make a decision. So if you're a walking robot and you need to decide in the next 10 milliseconds where you're going to move your foot, then you do not have time to go up to your creator's cloud server and ask a question about where you should put your foot. That computation, that sensing, computation, and action all need to happen within the robot because you just don't have very much time. So a good boundary question for this is, okay, so what's the time scale at which it might be okay for computation to be off robot? This is something that a lot of folks working on robotics foundation models are definitely contending with right now. And so it's not quite clear, and it depends on how good your internet connection is, but probably around 1 second. So if you have 1 second of time to make a decision, it's probably feasible that we could go to a cloud system and ask like what we should do. But if you need to make a decision in less than 1 second, and certainly less than 100 milliseconds about what to do, so typically how your robot moves in the next few milliseconds or the next half a second, or safety would need to be on board, because if you want to keep the robot safe, prevent it from breaking itself or others, we don't have time to go across a unreliable internet connection to make that decision. So large portions of the fundamental kind of motion of the robot and decisions about that motion need to stay on the robot. Where you see people playing with other possibilities is at a higher level of reasoning. So for instance, if you want your robot to bake a cake for you, or more, maybe pack a kit, one of each of these 10 items from these bins, and that's the command you give the robot, it might be okay for the robot to go ask DeepSeek or ask ChatGPT, some big bank of servers somewhere, how to break that down into a set of steps, which it can then follow. And it may even, if it gets stuck, it may be able to go and call for help. But it doesn't have time to go ask where it should plant its foot. And one last thing to say about this, and this gets really important for commercial deployment especially, is that as technologists, as software engineers, as researchers, we really love to think of the internet as being ubiquitous and always available and perfectly reliable. But whenever you try to deploy a real system, be it a self-driving car or a robot in a factory or someday a robot in a home, there will always be places and times where the internet access is not available. It drops. And going back to our earlier discussion of kind of irreversibility, it's really essential for a robot that when that happens, it doesn't necessarily need to be the case that the robot needs to be 100% functional for all the promises, everything the product could possibly do, but it needs to be safe, and it needs to be able to, importantly, get itself back to a state where it could become useful once again.
Yeah. And, you're talking about wanting robots to be safe. There are other folks who want robots to be dangerous. Yes. And I think, you can flip all of those things on your head if you're talking about the drone context, right? It's like, but it's not just that like Verizon sucks. It's that Russia has like electronic warfare energy being directed at you, trying to break that connection, and sort of the balance between, okay, we're just going to like press go on, 20 drones and like have them figure it out, versus, oh, maybe we would want the human to sort of orient to the left or to the right, or kind of having some dynamic there, and like the sort of levels of autonomy. There are upsides and downsides to like having the robot be able to make the decision.
That's exactly right. Yeah, and the more autonomy you ask for, from an intelligence perspective, like the scale of difficulty of creating a more and more autonomous system is kind of exponential. Right. So this is why Waymos are L4 self-driving cars and not L5 self-driving cars, because level 5 is just such a high bar, and you can provide incredibly useful, positive unit economics, changes the game on safety service, with just a little bit of human help, just a tiny bit.
What do humans do for Waymos right now?
I don't have any insider info on this, but it's my understanding that if a Waymo gets in trouble, if it identifies that it is in some circumstance where it doesn't quite know how to navigate out of a space or doesn't quite know where to take itself, that it's programmed to pull over to the nearest safest place it can find. So it does on board, it doesn't need to be able to figure out where's a safe place to pull over. And then it kind of phones home over a 5G or cell connection to like Waymo's central support center, and a human I don't think drives the car directly, because of those kind of real-time constraints we told you about moving the robot to also apply to a car. But I think that humans are able to provide the car with instructions for where it should drive or what it should do next at a high level.
Yeah. What level are we calling the Tesla robo-taxis, all of which have like a person sitting in the passenger seat?
Oh, that's a great question. I'm not a self-driving car levels of autonomy expert, but I think that in the taxonomy, full self-driving is somewhere between level 3 and level 4. because it is fully supervised at all times and has a human behind the wheel.
Yeah.
And
was a joke.
yeah. Oh, sorry, didn't take the
It's
bait.
okay. All right. So let's talk about, okay. So we have a sense of the possibilities. We have a sense of the challenges, the different sort of like technological trees that you have to climb. What is everyone in the field excited about? Why is there a lot of money and energy being poured in over the past few years to unlock this future?
So the reason people are excited is because there's been a shift in the way that we, in particular, build the software for robots. So I told you about how the hardware is becoming fairly mature. But even if you have the hardware, the way that we would previously build robots is kind of as single-purpose machines. So you either buy your robot hardware off the shelf or you build it yourself. But then in order to program the robot, you would employ a big room full of really brainy guys, a bunch of PhDs, guys and gals, a bunch of PhDs, to write a bunch of very specialized robotic software to tell the robot how to solve your specific problem. And this problem was usually not very general. It was usually something like, move these parts from one belt to another. Or in the case of maybe a much more advanced system, so this is something that would have been maybe state-of-the-art 2017 through 2021, Amazon and other logistics companies started engaging in this robotics where they want to make robots that could pick anything. Could pick anything off of a belt and put it into a box, pack any box, or pick anything off of a shelf. And the only variation there is essentially, where is the thing on this belt or in this box or in this cubby? How do I put my gripper around it? What shape is it? And then where do I move it? So from a human perspective, that's very low variation. I mean, this is the lowest of low skilled work. But this level of variation required, man-centuries of work to handle with a robot. Come to now, and the reason that everybody's so excited is that we are seeing a change in the way that we program robots. Rather than write these very specific applications for every little tiny thing you want to do, which obviously doesn't scale, and will put a very low ceiling on what is economical to automate, and who gets access to this technology, we are seeing robotics, much like software and AI, the programming robots turn from an engineering problem into a data and AI problem. And that's embodied AI. That's what robot learning is. So the idea instead is that you have some group of people somewhere, many groups of people, develop this robot learning software, this embodied AI software, primarily composed of a lot of the components that you're probably already familiar with from the LLM and VLM world, like a large transformer model and data processing and all of this stuff. Maybe a couple extra things that are robot specific. You build that once, and then when you want to be able to automate a new application, rather than hiring this big team that's going to build this highly specialized robot and hope that it works, you instead just collect data on your new application. You provide it with this embodied AI system, and you create this system that, given the data, can learn to do the new task. And the reason that this is exciting is that it would be exciting enough if you could do it for one task. But we're living in this world of LLMs and VLMs where we already have these systems which show that if I take thousands of purely digital tasks, summarizing a book, writing a poem, doing some math problems, writing Jordan's show notes for him, and you train one system to do all of these things, you get a system, a foundation model, we call it, that if you want to ask that foundation model to do a new task, this is in the purely digital world, you can give it just a little bit of data, or sometimes no data, just a prompt describing what you want to happen. And because that system has so much experience on doing many different tasks, you can kind of relate the data, the information, the training it has to the new task you'd like it to do. And with either very little data or no data at all, accomplish that task for you. So you're automating something that was previously not automated before with a very low amount of effort. And the hope of a robotics foundation model is that we could achieve the same effect, but with robots in the physical world. So if we can create a model that has data on many, many, many different robotic tasks and possibly many different robots, there's kind of contention in the field about this, that we could create the GPT of robotics, the DeepSeek of robotics, where if you had a robot that, already knows how to like make coffee and maybe sort things in a warehouse and clean up after your kid or something like this, and you ask it, today I'd like you to put together this piece of IKEA furniture for me. It may have never actually seen this piece of IKEA furniture. It may not have ever assembled something like that, but maybe you can like look through the manual a little bit and then put together the furniture. And that's a very probably fantastical, like, maybe 10, 20 years out thing, although we'll see. But if you imagine just the softer version of this, where if you have a business that wants to deploy robots, and all it needs to do is kind of apprentice those robots for maybe 1 week to 1 month of data collection. And then it can have a pretty reliable automation system for a task in that business. That could be really disruptive to the cost of introducing automation into many different spaces and sectors. So that's why people are so excited. We want the foundation model for robotics because it may be the thing that unlocks and allows us to put robots in many different places where they are currently it's not possible to put them because they're not good enough, or it's maybe possible, but it's just not economical.
So is all the excitement on the intelligence side, like are batteries basically there? Is the cost structure for building robots basically there? Or are there nice curves we're riding on those dimensions as well?
So there's an incredible amount of excitement in the hardware world too. I mentioned earlier that the history of robotics, particularly robotics hardware, is kind of riding the wave of other people funding the really hard tech innovations necessary to make robots economical. And this is still true today. So, for instance, you see a huge boom in humanoid robot companies today, and the reasons for that are a fewfold. So the first is that, and I gave you this vision of a robotics foundation model and a kind of a general purpose robot brain. Well, in order to really fully realize that vision, you still need the robot body. And it doesn't really help if you have a general purpose robot brain if you don't have a general purpose robot body, at least from the perspective of folks building humanoids. So the reason that humanoid robots are so popular today as kind of a deep tech idea is that if you could pair them with a general purpose brain with a general purpose body, now you have a general purpose labor saving machine. That chain of companies, that kind of group of companies is riding tons of progress in, like you said, battery technology, which is denser, higher power, cheaper, actuator technology. So this is, motors, which are more powerful, cheaper, in particular, speed reducers, which, so this is like the gearing at the end of the motor or maybe integrated into the motor. Traditionally, we're actually a very expensive part of any machine that was using electric motors. But there's been a lot of progress on making those speed reducers like high precision, much cheaper. Sensing is becoming much cheaper. A camera sensor, which used to cost hundreds of dollars, is now like the camera sensor, like in your iPhone, it's like $2 to $5, and that's like one of the most expensive components, right? You can imagine it's like totally economical to just like put them all over a robot, right? Yeah. So computation again, the computation, like the GPUs in like a modern robot might be worth a couple $100, which is just an unimaginably low amount of money for the amount of computation that is available there. So the robot bodies are also riding this wave of kind of other technologies in the world that are getting better, and they all are kind of dual use and they can be put into robots. And this is exactly, for instance, why maybe it is a good idea for Tesla to have an Optimus program to build humanoid robots, because a ton of the hardware that is in those robots is already being developed for other parts of Tesla. But it's not just inside Tesla. This is the case across the entire kind of technology economy.
Gotcha. Maybe now is the time to do a little like China versus the world detour. So sure. On a number of those different dimensions that you outlined, what are the comparative strengths and advantages of the China and the ex-China ecosystem?
Yeah. So I'm gonna separate this comparison probably in kind of research versus industry, because I think there's interesting bits on either side. And the short version is the robotics research in China is starting to become very similar to the West in quality. I'll tell you a little anecdote. So I started my PhD in 2017, and a big part of being a PhD student and a research scientist after that is you just consume tons and tons of research, kind of reams and reams of these dense 20-page PDFs with lots of information in them. And so you get very good at triaging, like what's worth your time and what's not, and you get very good at skimming. And you have to develop these heuristics for like, what am I going to spend my attention on? What am I going to throw away? What am I going to skim? What am I going to read deeply? Between 2017 and 2021, a good heuristic was that if a robotics or AI paper from China was from a Chinese lab, it probably wasn't worth your time. It may have been derivative, irrelevant, not novel. In some cases, it may have been plain plagiarized. It's not the case with everything, but during that period, it was a pretty good heuristic. So now, just in the last 2 years, I've really had to update my prior. The robotics and AI work coming out of China is like better every day. And overall, the caliber is not quite as high as US and EU and others in the West. But the best work in China, in AI, and in particular my specialization in robotics, the best work is rapidly catching up with the West. So today, when I see a robotics paper from China, I make sure I read the title and the abstract and really look in. And a good portion of the time, I save it. I'm like, I need to read this. And in a couple of years, the median quality may really be the same. And that we can talk about the trends. You talk a lot on this channel about the trends for why that might be, talent returning to China, people staying rather than coming to the US, government support, all this, but it's all coming together to really create an ecosystem. Similarly, as we kind of move away from research and into industry, I'll compare and contrast here. So due to the industry culture in China, also government incentives, the way funding works from provinces and VC funds, the Chinese robotics industry really tends to focus on hardware and scale. So they focus on physical robot production. And when I talk to a Chinese robotics company, there is always a story about putting intelligent embodied AI into real settings. But the way that they judge their success is usually in quantity of robots produced. It's a very straightforward industrial idea of what success is, which is a contrast with US companies, which are usually thinking about how can we create this breakthrough? How can we create a product that nobody else could create? That's not usually and how would we create a product where the real value is data and software and AI? There is a desire to have that data, software, and AI from the Chinese robotics companies I talk to, but it's very clear the business is formed to sell robots. And Chinese robotics companies, therefore, tend to focus on how to make a robot hardware cheaper and more advanced, and how to make a lot of them, and how to get access to the best parts, and how to get them into the hands of end customers, researchers, like upstream or sort of downstream companies that will be doing the intelligence work so that they can create this high volume channel of robot sales. To take a case study in kind of a darling of the industry, which is kind of covered on the channel. So like Unitree. So Unitree has been really good at this. Wang Jingjing and Unitree, what they essentially did is there was this open source design for this quadruped robot, so this four-legged robot called the MIT Cheetah. And what they did is they took that design, they perfected it, they really banged on it, made it production ready. I'm sure made tons of innovations in the actuators, the morphology of the robot, all this stuff. But they took it from something that you can make in a research lab at low scale to something that you can make on a production line in Shenzhen or just outside Shanghai, and then they sold it to anybody who would buy. And at the time, this seemed kind of dumb because there's really no market for robots. We're talking like 2016 now. And now they are like the player if you want to buy off the shelf robots. And so many, and they, what do they brag about in their materials? They brag about volume. They brag about how advanced their actuators are, how good the robot bodies are. And so this in industry, there's kind of this duality. Most of the American robotics companies, even if they're vertical and producing their own robots, they see the core of the value they're creating as being the intelligence or the service they will deliver to an end customer. So they're either trying to deliver intelligence as a service, like models or foundation models or kind of models as a service, like kind of like a ChatGPT type thing. You can query the model, or you can pay them to train the model. Or they are doing a fully vertical solution where they're going to deliver a robot into a place and it's going to do labor, but but the value they're providing is in hours of replaced labor. And if you look at the Chinese side of the pond, what you see is companies trying to produce really good robots.
So I've picked up a kind of energy of pessimism from a number of like robotics efforts in the West that China already has this in the bag. Where is that coming from, Ryan?
That's a good question. I think that if you are a pessimist so first of all, if you see AI as a race between the US and China, and you think it's going to be kind of like a winner take all thing, and you're pessimistic about the United States' or the West's ability to keep an edge on intelligence, then I could see how you could tumble into a very pessimistic case about the West's ability to keep an edge in robotics. Because as we discussed before, like a fully deployed robot in the world is essentially the combination of, software, AI, so intelligence, and a machine. The parts that are really hard to make are the intelligence and the machine. Famously, the United States and the West are not that great at they're good at designing, but they're not necessarily great at manufacturing really advanced machines cheaply. They can make really advanced machines, but not cheaply. And so if you see this as if you project this out forward and you think about a world where millions of robots are being produced and so then the marginal cost of the robot is very important, and the intelligence is essentially free, then I can see why somebody would believe that the country who can produce the most advanced physical robot hardware fastest, at lowest cost, would have a huge advantage. Because if you believe that there's no edge in the intelligence, that the intelligence is going to end up being kind of zero marginal cost, it's going to be free, then then you have a big problem, now don't you? So I think that's where the pessimism comes from.
All right, so we detoured off. We're going to come back. This idea of a foundation model to sort of unlock the future. I mean, we haven't. You did a pretty good job there, Ryan. But like, we're not in like ChatGPT October 2022 level excitement. I think for robots really like fulfilling their productivity generating potential. So, what do we need? What's on the roadmap? What are the inputs?
Yeah. So you want to build a great intelligent general purpose robot. You need to have the robot, the physical robot. And we've talked kind of at length about how robotics is kind of riding the wave of advancements elsewhere in the tech tree that's making it easier to build these robots. Of course, it's not quite done yet. There are great companies, Boston Dynamics and 1X and Figure, and many other companies who might be mad at me if I don't mention them, but like many other companies, Aptronic, right, Unitree, who are all trying to build great robots. But that's an engineering problem. And we can apply the standard playbook of scale, cost, and engineering to make them better. The key unlock then, if we have the robot bodies, is the robot brains. And we already have a way of creating robot brains, which is, again, you put a bunch of PhDs in a room and they toil for years, several years, creating like a really fairly dumb single-purpose robot. But that just doesn't scale, right? So what we need to get this kind of scaled impacts on productivity is we need a robot brain that learns and that can learn to do new things quickly. So this is why people are excited about robotics foundation models. How do we get a robotics foundation model? Great question. And everything I'm about to say is a hypothesis because we haven't created one yet. So we don't know exactly how. But the current thought is that creating a robotics foundation model should not honestly be that different from creating a purely digital foundation model, which is to say the name of the game is to train larger and larger models. Now, the model can't just be large in its own right. In order to train a large model usefully, you need lots of data. You need data commensurate with the size of the model. In LLMs, there seems to be this like magical point between 5 and 7 billion parameters where things start to get intelligent. That's when your GPT-2, GPT-3 behavior starts to show up. We don't know what that number is for robotics, right? But those number of parameters imply a certain amount of data. So what do we need to create the robotics foundation model? We need lots of especially diverse data on robots doing lots of useful things. And preferably that data, as much of that data as possible, should be useful things in the real world. So in other words, we need data and diversity at scale. And this is the big problem. This is the big problem for embodied AI. Because how does ChatGPT get its data? How does DeepSeek get its data? How does Gemini get its data? Some of it they buy, especially in recent years. But the first thing you do is you go ingest the entire internet, more or less. Billions of images, billions and billions of sentences of text. All of it is pretty much free or available to download at low cost. And the stuff they buy, they do buy very, very useful data, but the scale of what they buy is much smaller than what's kind of the unstructured just ingestion of all of this information from the internet. There's no internet of robot data. So, like I said, frontier models are training on billions of image text pairs. And today, the robotics foundation models with like the most data are trained on tens of thousands of examples. And those are kind of Herculean efforts of dozens, maybe hundreds of people. So that's the big chicken and egg problem. The big chicken and egg problem is if we had this robotics foundation model, it would be practical and economical to deploy robots in many different settings and have them learn on the fly, be collecting data. In robotics and also in AI, we've heard of this as the data flywheel, right? So you can get systems out of the world. Those systems, by operating in the world, they produce data. That data you can use to improve your system, which then gets you a better system, which means you can put more systems out in the world, generating more data, and your system gets better and better. So this is the flywheel we want to spit up. But you need to start with a system which is good enough to justify its existence in the world. And this is the quandary that robotics has. Another little note I want to make, because we talk about scale. Everybody talks about big data, as much data as possible. A consistent result from both purely digital foundation models and for robotics foundation models is that actually diversity is much more important than scale. If you give me millions and millions of pairs of exactly the same text or exactly the same task or millions and millions of demonstrations of a robot doing exactly the same thing in exactly the same place, that will not be helpful to my system to learn. So my system needs to not only see lots of data, but that data needs to be on many different things. And that throws another wrench into the economics, because you can think about the economics of like deploying 100 robots into a space and having them do a task like picking packages or
yeah. It's like, okay, so like if we have the robot that can fold the laundry, then it can fold the laundry. But will folding a laundry teach you how to make the IKEA furniture?
Right.
Probably not. Right.
Yeah. So economics like scale, but we want the opposite of that. We want a few examples of lots of different things, which is the most expensive way. Right. It's the most expensive possible way you could organize something.
So, I have a 1-year-old, and watching her build up her like physics brain of just like understanding the different properties of things and like watching her fall in different ways, but also kind of the never the same way twice. Like if you just put a new object in front of her, like for instance, we have a Peloton. She like fell once because she put her weight on the Peloton wheel and the Peloton wheel moved. She has not done that again. And she is 1 year old and really dumb at a lot of different things. And just, I don't know.
I'm sure she's a genius.
Human is kind like human beings are kind of amazing.
They're really good.
And to be able to, it's like the language, like because the robots can't do it yet. I mean, I think like because we have ChatGPT, maybe like figuring out speech is less of a marvel now. But the fact that evolution in our neurons or whatever, and particularly like because you come into the world not entirely getting all of it, like watching the data ingestion happen in real time has just been a real treat. I don't know. Do people like study toddlers for this stuff, or what's
man, and in like robot learning research, like I'm a junior professor who just had my first kid, and now all my lectures are going to be about watching my kid and how they learn is like such a trope. Like it's not just you. It's not just you. Like, but it's we can learn things from this. We can learn things from this. Like, first of all, kids are not purely tabula rasa. They do know some things about the world. Yeah. Kids are always learning. They're always learning. So, you think, oh, my kid's only 1 or 2 years old. But imagine 1 or 2 years of continuous waking, HD stereo video, complete information on where your body is. You're listening to your parents say words. You're watching parents or other people in the world and other kids do things. You're observing the behavior of the world. And this is really the inspiration for why up through about 2022, let's say, me and other folks were so enamored with the idea of using reinforcement learning to teach robots to do things. And reinforcement learning is a set of machine learning tools that allows machines, AIs, robots to learn through trial and error, much like you described your 1-year-old. What's been in vogue for the last few years has been a turn towards imitation learning, which is essentially we show the robot over and over again different ways of doing things. And the reason that imitation learning has been in vogue is that, again, it's this chicken and egg problem. Like if you're not very good at things, then most of what you will try and experience will not teach you a whole lot. And if you're a 1-year-old bumbling around the world, that's like, okay, you have a good 18, 20, 30 years. I mean, there's a lot of things I don't know how to do. I'm 35 and still trying to figure out things, right? But like we have these like very high bars for robots. Like we want robots to be really good at things. The other thing is that it's very expensive, dangerous, and difficult to allow a robot to just flail around the world and break things and people in itself, and just do reinforcement learning there, and really not practical. But it is practical for us to have a bunch of humans show robots what to do. Well, maybe a little bit more practical than reinforcement learning. What this eventually all boils down to, like how to solve this chicken and egg problem I told you about, and nobody really knows what the solution is that there are a few things we can do. So one is we don't necessarily have to start from scratch. So some of the recent exciting results, and where a lot of the well of excitement has started to really blow up, was that the teams that I worked on and myself and teams that I worked on and collaborators and other labs were able to show that if we start with a state-of-the-art vision language model and we teach it how to do robot things, it can take the knowledge it already has from the purely digital world, such as like, what's the flag of Germany? And it can use that for robotics. So imagine you give data to one of these models that shows you how to pick and place things. You can just pick things off the table, move them other places, put them down, whatever. But let's say it's never seen a flag before, or it's never seen like the flag of Germany before, and it's never seen a dinosaur, but it's picked up stuff that's kind of a similar size. Well, you can say, hey, please pick up the dinosaur and place it on the flag of Germany. And neither the dinosaur nor the flag of Germany were in your robotics data, but they are kind of part of the VLM training. And myself and my collaborators and other people showed that you can, first of all, can identify, oh, this is a dinosaur over here. I can use the information it already had on picking up previous things to pick up that little toy dinosaur. And then it can move it over to this flag sitting on the table, which is like the flag of Germany. So one tactic is don't start tabula rasa. Start with something that already knows something. Another tactic, and this is where all those dancing videos you see, like all those cool like dancing videos from China and like robots running and like doing all these acrobatics. So that comes from training robots in simulation with reinforcement learning. If the physicality of your problem is not too complex, so if you're just trying to walk, I know I say just, but like merely walking or kind of moving your body around, it turns out modeling the physics of walking or kind of dancing around
on concrete on a flat surface, not like
it's like
hiking around Bakhmut or something.
Yes, exactly.
Levels to this.
Right. So like we can model that pretty well on a computer, and then we can do 99% of the training in simulation, and then have this robot doing these cool dance around and stuff like this. And we may be able to extend that framework to a much more difficult physical challenge, like, pouring tea and moving things around and assembling things. But those physical interactions are much more complex. But you could imagine extending that framework to that. So the second one. So you got don't start from scratch. You have simulation. The third tactic you could imagine is get data from somewhere that isn't robots, but it's like close. So this has been a canard for years and years in robot learning. Like everybody's like, I want robots to learn from watching YouTube videos. And there's a number of really difficult challenges to do that. But the basic idea is that either from a first person perspective, so you're looking through the eyes of the human, or from a third person perspective, so you're watching a human do things, you may be able to extract information from data we already have, like lots of videos of people doing things about how to do the tasks. Now, what I just described is like definitely state-of-the-art frontier research, and nobody quite knows how to do it. But those are some of the hopes. Then, the community also tends to separate into camps over who thinks the best, and even companies around like who thinks which strategy is going to be the one that wins. Then there's always the pour a giant pile of money on the problem strategy, which is what the gold standard is, what we know works right now, and what many people are increasingly willing to put up capital to do, is to simply build a bunch of robots, hundreds or even thousands, put them in real places, put them in factories, put them in laundries, put them in logistics centers, put them in restaurants, pay people to remote control those robots to do the task that you want, collect that data, and use it to train your robotics foundation model, and hope that the rate at which that hope that you don't run out of money before you reach that magic knee in the curve, that magic knee that we see in every other foundation model, where when the model gets big enough and the data gets big and diverse enough, we suddenly have a model that learns very quickly. And so there is a whole arms race around how can folks deploy capital quickly enough and in the right way to try to find that knee in the curve.
Is Waymo like an example of throwing enough money at the problem to get to the solution? Like
Great example.
How do we categorize that?
Yeah, so Waymo and other self-driving car efforts, like full self-driving, this is one of the things that gives people faith that this might just work. Because if you step into Waymo today, you are being driven around by, at its core, a robotics foundation model. So there's a single model where camera and LiDAR and other information from the car come in, they get tokenized. Decisions are made about what you should do next, and out pops the actions of where the car should move. Now, that's not the end of the story. There's layers and layers of safety and decision-making and other checks and balances within a Waymo to make sure that the answer that comes out is a good one and it's not going to hurt anybody. But the core process is collect data on the task, in this case, moving around a city in a car, use it to train a model, and then use that model to produce the information you want. So yes, exactly. Self-driving cars have been a long road, but the success of using this technique for self-driving cars is what's giving people a lot of faith. Let me rain a little bit on your parade. So there's hope, but then here's why it's hard. From the perspective of robotics, so a self-driving car is absolutely a robot. And from the perspective of robotics, a self-driving car has a very, very simple job, and it only does one task. The job of a self-driving car is to get you, Jordan, and maybe your companions, from point A to point B in a city, according to a fairly small set of traffic rules on a fairly predictable course, not completely predictable, but roads are kind of the same. And to do so without touching anything. That's it. That's all you got to do. You just get point A to point B, don't touch anything. The robots that we're talking about here, these general purpose robots that we want to build, their value comes from being able to do thousands of tasks, or at least hundreds with not that much training data. So that's one axis of difficulty, is now we have to do lots of different things, not just one thing. The other additional difficulty is that part where your goal is to not touch anything is really super convenient, because every car, more or less, from a physics perspective, drives the same. So the physics of what the car is doing.
And they're trying to avoid you. They're on your
side.
And
they're trying to avoid you. Just don't touch anything.
Either.
Whatever you do, like don't touch anything. Don't touch anything, right? As soon as you touch things, the physics become a lot more complicated. And so it's much more difficult for the machines to make decisions about what to do.
Interesting.
And the usefulness of a general purpose robot is that it touches things. Like, unless it's going to just rove around your house or your business and like, really pump you up and tell you how cool you are and tell you jokes, like it's going to have to touch things to be useful. And so those are the two big things, the big jumps that we'll need to make from kind of the self-driving car era to the generalist robotics era. Many different tasks, and we need to touch the world.
Yeah, I don't know, Ryan, what do you want to tell Washington? Do you have like policy asks to help create our flourishing robotics 21st century?
So my policy ask would be that policymakers and people who are informing policymakers really learn about the technology before you start worrying too much about the implications for labor. There are definitely implications for labor. There are also implications for the military. But the history of technology has generally been that most new technologies are labor multiplying and labor assisting. There's very few instances of pure labor replacement. And I worry that if a labor replacement narrative kind of takes hold in this space, it could really hold back likely the West, but also, the entire field. And as of today, I don't think a labor replacement narrative is actually very well grounded in reality. So that would be my ask is educate yourself and think about a world where we have incredibly useful tools that make the people that are already working in jobs way more productive and safer. Because the level of autonomy and technology required to create complete labor replacement in any of the jobs or sectors we talked about is incredibly high and very far off. It's completely theoretical at this point.
Who are the companies in China and the rest of the world that folks should be paying attention to?
Yeah. And I have to say that the Chinese space is gigantic. So I'm only going to be able to name a few from there, but there are great resources online if you search for Chinese robotics ecosystem. In the West, in the US, I think I would divide the companies that are really pushing in this space into kind of two camps. One are typically hardware-forward robotics companies, so companies who think about what they are doing as building the robot and deploying it. These tend to be vertical-ish. I'll call them vertical-ish because almost all of them do want to build their own embodied AI, but they approach it from a build the whole robot, build in the AI, deploy the robot space. In that bucket, you have Figure AI is kind of a vertical humanoid robot builder, which also builds their own intelligence. There's 1X Technologies, which focuses on home robots, at least right now. Boston Dynamics, famously, first mover in the space, and they've been focusing on heavy industrial robots with the Atlas E. Tronic, which partnered with Google DeepMind, also focusing on light industrial logistics cases right now. Tesla Optimus is probably the most well-known bid in the space, and there's lots of rhetoric from Elon about how many robots they will make and where they will deploy these and how they will be in homes. But it's pretty clear that right now the first value-added Tesla will be helping automate Tesla factories, and in fact, a lot of the capital in this space and a lot of the prospective customers are actually various automakers who are looking to create better automation for their future workforce. And then you also have actually Apple moving into the space now. They have a very early effort at Apple to build humanoid robots. So those are hardware forward. In kind of the robotics foundation model, software forward bets, and these tend to be, I'll call them horizontal-ish. So some of them may have bets on making like their own hardware, but the thrust of what they do is very foundation model AI focused. You have, of course, my former employer, Google DeepMind, has the robotics group and Gemini Robotics. And NVIDIA also has a group doing this, helps them sell a lot of chips, for instance. And then there are startups. So there's Physical Intelligence, which is founded by several of my former colleagues at Google DeepMind. They're out of San Francisco. Skilled AI, some CMU guys. Generalist AI, also some former colleagues of mine. And recently learned that Mistral has a robotics group. A few other shout outs for the Western groups. There's a company called Dyna, which is looking to use the same technology to automate small tasks as quickly as possible. They're like, you guys are all getting way too complicated with all this. Let's just like fold some napkins and make some sandwiches and do some other stuff. And then there are a couple groups which, your audience may want to be aware of, but we don't really know what they're doing. But Meta and OpenAI certainly have embodied AI efforts that are rapidly growing, but nobody quite knows exactly what they're doing right now. Now in the China space, in China, there is partially because of all the trends we talked about, also because of a lot of funding and encouragement from the government because of Made in China 2025. There's been this explosion of companies seeking to make humanoid robots specifically. And so most well known is Unitree with the H1 and G1 robots. But there's also companies for Your Intelligence, AGI Bot, Robot Era, UB Tech, Engine AI, Astrobot. I mean, there is just a whole zoo of companies which are in China trying to make great humanoid robots, and they're trying to leverage that, Shenzhen, Shanghai-centered manufacturing base and the incredible supply chain there to make the hardware.
Let's talk. How do robots people talk about timelines?
I mean, it's as diverse as any other field. Some people are really optimistic. Some people are more pessimistic. Generally is correlated with age or time in the field. But I know kind of the question you're asking me, which is like, when is it coming? Let's kind of ground real quick. What do robots do today? Well, they sit in factories and do the same thing over and over again. Very little variation. Then maybe they sort some packages, which is like a little bit of variation. Slightly more intelligent robots will kind of rove around and inspect facilities. Again, they don't touch anything. They just take pictures. And then, of course, we think about consumer robots. What's the most famous consumer robot? It's a Roomba, right? So it has to move around your house in 2D and vacuum things and hopefully not smear the dog poo everywhere. So that's robots today. What's happening now and what we'll see in the next 3 to 5 years? So I'll say this is this bucket I'm saying is kind of like, this is possible with current technology. So there's no giant technological blockers, but it may not be yet proven to be economical. And we're still kind of in like pilot phases or trying to figure out like, how can we turn this into a product? And so I think the first place you're going to see more general purpose robots, maybe a lot of humanoid form factors, maybe slightly less humanoid, maybe like wheels and arms kind of robots. I'm going to see them in a lot of logistics, material handling, and maybe light manufacturing kind of roles. So for instance, like machine tending is one where you take a part, you place it into a machine, you press a button, machine does a thing to the part, open the machine, pull the part out. And you may also see some like retail and hospitality back of house. So what I'm talking about here is anywhere where a lot of stuff needs to be moved, organized, boxed, unboxed, sorted. This is an easy problem, but it's a surprisingly large part of the economy, and it pops up pretty much everywhere. So half or more of the labor activity in an auto plant is logistics and material feed. So this is stuff getting delivered to the auto plant, moved to the right place, ends up at a line, someone picks it up, places it into a car. So more than half of car manufacturing, half or more car manufacturing is that. And it's actually getting worse because people really want customized cars these days. Customizations on cars are where all the profit margin is. And that means that instead of like Model Ts running down the line and every car is exactly the same, actually every car running down the line requires a different set of parts. And so a ton of labor goes into organizing and kitting the parts that you want on each car and making sure they end up at the right car. 10 to 12% of the world economy is logistics. Another 15 to 20% is manufacturing. So this is already a huge impact. And all you're asking the robots to do is just move stuff. Just pick something up, put it somewhere else. You don't have to assemble it. You don't have to like put bolts in. No, just move stuff. So I'm going to say next 3 to 5 years, you're going to see pilots are starting today. And you're going to see a lot of attempts both in the West and in China to try to put robots general purpose robots into material handling and show that this template we've described with robotics foundation models can work in those settings. Now, if that works, if the capital doesn't dry up, if the researchers don't get bored and say, I'm going to go be an LLM researcher because, Zuck's going to give me $1 billion, then maybe in the next 7 to 10 years, if we have some more research breakthroughs, we may be able to see these robots moving into more dexterous and complex manufacturing tasks. So think about like placing bolts in, assembling things, wings on 747s, putting wiring harnesses together. This is all really difficult. You could even imagine at this point, we're starting to see maybe basic home tasks, maybe like tidying, loading and unloading a dishwasher, cleaning surfaces, vacuuming.
Massage? When's our massage?
Oh man, massage. I don't know. Do you want a robot to press really hard on you? Like, would you trust that?
No. I mean,
exactly.
Yeah, we're probably that's our 10 to 15 year.
I think that's the next, anything that has a really high bar for safety, interaction with humans, compliance. So it's like healthcare, massage, personal services, home health aid. Not only will that kind of stuff require orders of magnitude more intelligence than we currently have and more capable physical systems, but you also really start to dive into serious questions of trust, safety, liability, and whether the level of reliability and faith you want in a robot to have a robot roving around your house and your 1-year-old kid and have it not fall over, I think requires a really high level of intelligence and also a really high level of trust. And so that's why I say that's like a question mark. We don't quite know when that might happen. It could be in 5 years. I mean, I could be totally wrong. Technology changes real fast these days, especially. And people are more willing than I'm usually expecting to take on risk. Autopilot and full self-driving is a good example. But I think that one thing that the current generation of robotics researchers, generalist robotics researchers, startups, companies are trying to learn from the self-driving car era. And so maybe one reason to be optimistic is that exactly because of this safety element, self-driving cars moving around a multi-ton machine around lots of people and things, it could kill or break. You have people inside of it who you could kill. The bar is really high. It's almost like a commercial airplane. Like, the system needs to be so reliable, have so much redundancy, and the society and regulators and governments have to have so much faith that it is safe. It is both safe and kind of a positive cost-benefit trade-off, that it makes it really difficult to thread the needle and make something useful. And what that does in practice is it takes you up the difficulty and autonomy curve we talked about, and it pushes you way up here. It's going to be really, really high levels of autonomy to be useful. It's kind of a binary. Like, if you're not autonomous enough, you're not useful. But these generalist robots we're talking about, they don't necessarily need to be that high up the autonomy difficulty curve. If they are moderately useful, if they produce more than they cost, and they save some labor but not all, and you don't need to modify your business's environment, your home, your restaurant too much in order to use them, and you can operate them in a manner that doesn't have to involve large amounts of safety. So, for instance, if you're gonna have a restaurant robot, probably shouldn't start with cutting vegetables. Don't put big knives in the hands of robots, right? But there's lots of other things that happen in a restaurant that don't involve big knives in the hands of a robot. And so I think one of the bright spots of the current generalist robotics kind of push and investment is that we believe that there's a much more linear utility autonomy curve. Like, if we can be half autonomous and only need to use 50% of the human labor we did before, that would make a huge difference to many different lives and businesses.
That seems kind of, I don't know. Is that middle of the road? Is that pessimistic? Like, where are our humanoid robot armies? and you know, like something that can change a diaper?
I think it's a question of when, not if, we will see lots of general purpose robots landing, especially in commercial spaces. Logistics, manufacturing, maybe even like retail back of house, maybe even like hospitality back of house. The trajectory of AI is very good. The machines are becoming cheaper every day. And there are many, many repetitive jobs in this world that are hazardous to people, and we have a lot of difficulty recruiting people to do that are not that difficult to automate. So that I think is baked in. And so if that's a robot army, if you're thinking about hundreds of thousands, maybe even over the course of 10 years, millions of robots working in factories, likely in Asia, possibly in the West, I think that we will see it in the next decade. The big question mark is, how advanced will we be able to make the AI automation? So how complicated are the jobs that these machines could do? Because technology has a habit of working really, really, really well and advancing really quickly until it doesn't. And so I'm not exactly sure where that stopping point will be. If we're on the path to AGI, then man, buckle up. Because the robots are getting real good and the AGI is getting real good, and maybe it'll be gay luxury space communism for everybody, or maybe it'll be iRobot. But I think that the truth is probably somewhere in between, and that's kind of why I started our discussion talking about how robots are the ultimate capital good. Because if you want to think about what would happen if we had really advanced robots, then just think about what would happen if your dishwasher loaded and unloaded itself, or or the diaper changing table could change your daughter's diaper. I think a good dividing line to think about is that home robots are very difficult because the cost needs to be very low. The capability level needs to be very diverse and very high, and the safety needs to be very high. So we will require orders of magnitude more intelligence than we have now to do home robots. And if they do happen, I think that we're probably 10 plus years away from really practical home robots. But in the industrial sector, and therefore like the military implications we talked about, I think it's baked in at this point.
I mean, it's hard, like as someone who has, confession, not worked in a warehouse or logistics before, I think it is like, it is a sector of the economy that a lot of, Washington policymaking community just like doesn't have a grasp on. And like, automating truckers and automating cars, like that is like, doesn't take many intellectual leaks, but sort of the, like thinking about the gradations of different types of manual labor that are more or less like computationally intensive, is a hard thing to wrap your head around if you haven't really sort of hard. Like seen it in action, right?
I mean, this is why on the research teams we take people to these places. Like we go on tours of auto factories and logistics centers because your average robotics researcher has no idea what happens in the Amazon warehouse. Not really. Right. No. There are also, so for your listeners might be interested, there are also actually incredible resources for this provided by the US government. The Department of Labor has this ontology of physical labor. I think there's 50,000 or more entries. And it's every physical task that the Department of Labor has identified that anybody does in any job in the United States. And it gets very detailed, down to like cutting vegetables or screwing a bolt.
We're going to have to link to that in the show notes. Any more? This is kind of what I wanted to close on, Ryan, is like, how can people follow this space? Like, what would you recommend folks to read or consume?
Yeah, well, of course, you should subscribe to China Talk. Lots of great robotics coverage. And the semi-analysis guys also seem to be getting into it a little bit. Other than that, I would join Twitter or Blue Sky. That is just like the rest of the AI community, that is the best place to find kind of original, raw content from people doing the work every day. And if you just follow a couple of the right accounts, I'm not going to name any because I don't want to be repping anybody's Twitter accounts, but maybe we can include some links in the show notes. If you follow a couple of the right accounts and then you start following who they retweet, over time you will definitely build a feed where when the coolest new embodied AI announcement comes out, you'll know in a few minutes.
Do you have a favorite piece of fiction or movie that explores robot futures?
Oh, I really like Wall-E. Wall-E and
Why?
Big Hero 6. I like friendly robots.
All right. I think that's a nice place to end. Ryan Julian, thank you so much for being a part of China Talk.
Thank you so much, Jordan, for having me.